time to get this class started, and there were several questions. Several people reminded me that I did not give people the key to the aptitude test. So, well, maybe that was part of the aptitude test too, is to see whether the person will ask, but what are the answers to the aptitude test? All right, so let's go ahead and quickly go over this. I don't really have the key on hand, so I'm just going to do this as we go along here. 19, 23, 27, 31, 35, 39, they're all incrementing by 4. So the next one should be 43. 3, 4, 5, 3, 4, 5. The next one would be 3 because it's a repeating pattern of 3, 4, 5. 53, 58, 54, 59, 55, 60. So the next one is going to be 56 because it is going like that. Next one is 11, 14, 18, 23, incrementing by 3, 4, 5, 6, 7. So the next one will increment by 8, so it will be 44. Okay, this one is 23, 19, 24, 18. So the 23, 24, 25, so the next one will be 26, which is E here. 27, 25, 28, 25, 29, 25. So the 25 is constant. The other one is incrementing by 1, so the next one will be 30. 4, 11. Okay, that's a 7, 5, 3. Okay, that's not it. Oh, okay, never mind. Okay, I was misreading. Okay, that's 7, 5, 3.
7, 5,
okay.
3. So
And
3
that
up
would be,
there would be what, 34?
and then it jumps to what?
It goes
That's a 7 again.
That's 7, 5,
Yeah,
3,
7, 5, and then
5,
another 3, so it'd be 34. Yep. 7, 13, 5, 5. Oops.
Yeah.
This is
5,
5,
9,
9,
6.
6.
Feel good about this test already.
Sorry?
Feel good about this. If I can pick it up faster than the doctor, the first one was 6.
Okay, so it's basically every other one. So it's
Incrementing up 1.
yep. So this is 6, 9, 6, 9, 6, 9. So it'll be 52. Okay, 13, 17, 4, 4,
I like
4,
4. Okay, now we go back another, and then 3. So the next one will increment by
3.
But this is decrementing back to 19.
So
This is decrement again. So it will continue to
16.
16.
it'll be 16.
Yeah.
It starts going down 3.
Yeah.
It's going down 3, 3 here. So the next one will be 3.
Yeah.
Okay.
16. And then it'd be 16.
But this one's kind of interesting because 36
Yeah.
minus 12 is 24. 24 minus 8 is 16. So the next one's going to be 16. That's my guess.
A little bit different. I think I got the same answer.
16 here. No?
Which one?
This one here, number 10.
3 times 2 divided by 1. And divide by 3 times 2.
That's what I did.
Should be 16 now.
Yeah, that's the same way I did it.
Yep. But that's also the pattern of 36 minus 12 is 24. 24 minus 8 is 16. So 16 da 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 da. This one is 2, 3, 4, 5, 6. So increment by. Oops, nope. I take it back. 2, 3. Okay, 2, 3, 4, and then 5. Back to 2. So maybe another 3. So it'll be increment by 3 again. 72 is the answer.
Isn't it 4?
Huh?
58 plus 62.
Okay, increment by 2, increment by 3, increment by 4, increment by 5, increment by 2, increment by 3. 69 plus 3 is 72. And then here we have 1, 4, 2, 8, 4, 16. So we have to go for 1, 2, 4. The next one is going to be 8, which is B. 12, 14, increment by 2, increment by 5, and increment by 7, 2, 5, and then 7, so that will make it 40. So in other words, the patterns, actually, they only have certain types of patterns, so you have to kind of see which template it matches. And once you find the template that it matches, the next number is really just according to that particular template. Yep. Yep.
Is it only addition and subtraction?
No, they have just usual patterns like 1, 3, 5, 1, 3, 5, and so on. Yep. Yep. So I'm gonna stop here. So we'll do one sheet per day. So that would be kind of cool. Yeah. Warm up. Well, we can also do warm up here. Go to the power server and go to the WordPress here.
Whose baby is this?
Whose baby is
Starting to
this?
seem less like a computer bus.
Suddenly it sounds like a Jerry Springer.
Exactly. Something like that, yeah.
Well, this one is interesting because the baby has 2 candidate fathers. This one or this one. So do you like this guy or this guy? If they duke it out on stage like Jerry Springer, who's gonna win?
Duke it out.
We'll call the security. Call security. Well, these two are both important figures in the history of computer science. Without John von Neumann, there would not be a lot of things that we have today, including the hydrogen bomb. I'm not kidding.
It's a pro and a con.
He just look at the fields that he has significant contributions to. This long list here are the fields that he has major contributions in. So everything from math, geography, topology, numerical analysis, all kinds of physics, quantum physics, and so on, computer science, mathematics, statistics, economics, and so on and so forth. The list just keeps on going and going. Okay?
Well,
and the amazing part, there are geniuses in our times, okay? Albert Einstein, okay, which actually overlapped with this guy when they were both teaching at Princeton. And this guy likes to play loud music when he's working. And Einstein was actually kind of maybe not next to him, but along the same hallway and had problems with his loud music at Princeton. If you read his bio, okay, it's kind of long. I'm not going to read the whole thing. If you read his bio, a lot of the other physicists, mathematicians, computer scientists, and so on and so forth, big names, important people, smart people, would basically compare, and whenever this name is mentioned, they would say, I could never catch up with him. Okay, I would say something, blah blah blah, and he would take that and expand it for an hour into some complete, full-fledged, theory. So he is way ahead of everybody. He, in terms of his intelligence, he's just way out there. Okay, he's not famous for one thing. He's not famous for relativity. He's not famous for quantum physics. He's not famous for theory of computational machines. He's famous for a lot of different things. The really sad part was, he died fairly early. He was only 54 when he died, and most people believe that he died of cancer related to his participation in the hydrogen bomb test. So that's John von Neumann. Without him, we would not have the computer architecture that we have today, having memory as a separate thing, the processor, and computers that can be reprogrammed without taking parts out and rewiring all the parts. Okay, he is the first one who came up with the idea of a computer that can be programmed without rewiring. Okay, so that's one big figure in computer science. Alan Turing is the other one. Without Alan Turing, World War II might not have ended the way that it did. It might have drawn on for a little bit longer, because he was the main contributor in terms of theory and also the design of the Colossus computer mainframes. And those computers were used to decipher encrypted German transmission at the end of World War II. They have been doing that by hand, manually, for many, many years during the war, and be able to do it because the German were using, I think, 4 encryption disks in their Enigma machines at the time. But when they threw in the 5th one, it became infeasible for people to do it by hand. And he basically came up with the theory behind how to use a machine to do it automatically, and also helped design the first electronic computer for that purpose. So without him, we would not have the computational theory in computer science that you guys will still have to take when you go to a 4-year university pursuing your computer science degree. We would not have regular expression. Some of you, many of you probably don't know what is a regular expression, but if you use Perl or any type of scripting language, it's a very important construct, and he basically came up with the basic theory behind regular expressions and all the other related type of things. And this guy also died early, and way earlier than the other guy. He was born in 1912 and he died in 1954. So he was only 42 when he died, when he committed suicide. And the way he committed suicide is also not the usual way. Okay, you have to read about it to find out how unusual this guy really was.
4th paragraph.
4th
He
paragraph.
was prosecuted for homosexuality 2 years before his suicide.
Right, but he also used a poisoned apple, right? And I think it's borrowed from the Cinderella.
Snow White.
Snow White, yep. Not Cinderella, Snow White. So it's interesting, definitely an interesting individual. But if he had not committed suicide, this guy would have been able to contribute even more to computer science. If he did not if he did not end his life early. So anyway, interesting read in either case. They're both very interesting individuals. On certain levels, you can say they cannot be more different as individuals. And if you read the bio, you will also find that they are also kind of common. They have common traits as well. And I'm not going to spoil it. You have to read it to find out for yourselves. All right. So now we're back to the kind of more boring stuff of this class. And we'll talk about variables. Okay, we are done with variables. So you have your assignment statement, homework assignment already active, and today I'm going to stack on another one. So you have 2 concurrent homework assignments that you have to get done on conditional statements. So the first thing I will do is I will show you your conditional statement homework assignment, and then we'll go ahead and take a look at conditional statements and how do we trace conditional statements. So this is your homework assignment. Okay, the pseudocode looks like this. It is a single conditional statement, a little bit like the find maximum pseudocode, but not exactly the same. But the one thing you have to pay attention to is there are 3 traces that you have to do in this case, because you have 1 test case here, 1 test case here, and 1 test case here. So there are 3 additional sheets that you will have to trace your algorithm. It's not going to be very long, okay? It's not going to be very long because I'm going to show you how to trace conditional statements today, and you will see that, oh, okay, there's really not much to it. So are there any questions right now regarding the new homework assignment? We will talk about it today, okay? I will give you examples of how to trace conditional statements, and I will also make sure that you understand the convention that I'm expecting in these homework assignments. Is that okay so far? Okay. So let's move on, and in this class, I believe we are a little bit further ahead compared to the other class, compared to the 9 o'clock class. I drew the picture already. We talked about the pseudocode. So what I'll do today is I am going to use an example to illustrate it, and also to show you guys how to trace an algorithm that has a conditional statement. So I'm gonna hide the 9 o'clock class one. Okay, so I'm gonna turn off the ones that I don't need anymore. We can reuse this algorithm. So let's go ahead and reuse this one. We'll do all the traces from scratch. Okay. And go back to the pseudocode. as the trace, and we can close that. There we go. Okay, so we will go ahead and get started with this good pseudocode on the left-hand side, and we'll do the trace on the pseudocode is on the left-hand side, the trace is on the right-hand side. Nope. Okay, so the first thing you want to do when you look at a conditional statement is to understand what it means. Okay. In other words, in your mind, you will have to map the representation in pseudocode to the logic represented by that pseudocode. At the beginning, if you have no prior exposure to programming and you kind of feel that, well, if I just read the words here, I don't really quite know what to do with it, then the first thing you can do is to remember this template here. I'm just going to draw it on the whiteboard. So if you have a conditional statement, it always looks kind of like this. Okay, I'm going to use the convention in Scratch using a hexagon to represent an expression that will give you either a true or a false value, otherwise known as a Boolean expression. Okay, so most conditional statements looks like this. It starts with a line that looks like this, and then I'll have there will be a block of code here, okay, and then you'll see the word else, and then you have a different block of code here. And I'll use a different color in this case for the other block of code. And in pseudocode, in this class, and also in actual Visual Basic, you will also see the word and if to mark the end of the conditional statement. So this is a fairly general template of a conditional statement in pseudocode and also in some actual programming languages. So when you see something like that, what you want to do is to say, okay, when I see something like this in pseudocode or in Visual Basic, it is representing this kind of trail path. So it is a trail path that has a fork or a branch with two sides. The two sides will merge like so. So you have to enter from the top, exit at the bottom. At some point, you can make a branch. When you take the branch, you have to decide which way to go. In order to determine which way to go, you will have to take the Boolean expression here, which is also called a condition, because the condition will be basically here, it is a question. Is it true or is it false that blah, 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 blah? Okay. If it is true, you follow this path here, and this path is representing the blue rectangle, okay? The code between the if and the else. If the condition evaluates to a value of false, then you have to follow the other path. The other path is represented by the black rectangle, basically the code between the else and the and if keywords. But it doesn't matter which way you go, you still have to merge at the end before you get out of the conditional statement. Okay. So are there any questions about this part here, which is just in general, when you see this type of pseudocode, in your mind, you have to reconstruct the logic represented by this trail path. Really quickly, most people do not need to go through the picture anymore. Once they read the pseudocode, they kind of know what to do. Okay. But initially, if you feel that a picture would be helpful, that would be the picture that I would draw to kind of remind myself what to do with a conditional statement. Are we doing okay so far with that picture? I'm going to leave that picture on the whiteboard because as we go through this code here, we want to have a kind of idea of, okay, but where do we go now? What do we do next? All right, the first thing we know about tracing pseudocode that has conditional statements is we now have an additional column that is labeled comments. The reason why we have an extra column labeled comments is because when we evaluate the condition on line 1, it doesn't have any side effects that is observable. In other words, it doesn't change any value. X is remaining exactly the same as before. And so there's no change in X. It doesn't do anything else. So how can we document or remember the fact that we evaluated that condition and the result of that condition is why we choose to go one way or the other? So that's why we have a column that says comments, because it's really just an annotation to remind ourselves what did we do and why do we choose to go this way or the other way. So are there any questions at this point? Nope. Okay. So There we go. We will start execution on line 1. So once again, on line 1, we are not making any changes to x because all we want to do is to compare x to 0 and see whether it is true or false that x is less than 0. So if you want to, you can just say that x retains its previous value of 10. Now at this point of this class, I'm going to say, well, in all future traces, there will be a lot of same value, same value, same value. So if you don't want to be tedious, you can just leave it blank. In other words, a blank cell in a column corresponding to a variable means no change to the previous value. That's all it's going to say. Okay, but we do have something else to do. In the comments column, you will need to repeat the expression itself. So in this case, the expression is x is less than 0. You will have to repeat that expression here. X is less than 0. But then you also have to tell me, after you evaluate it, is it returning a value of true, or is it returning a value of false? So in this case, is it true or false that x is less than 0? False, because x has a value of 10 right now. 10 is less than 0 is false. All right. So the next question is, what is the next line that we are going to trace? Well, if you look at the picture, okay, if you look at the template here, if the condition is false, okay, if you look at the trail map, if the condition is false, we're going to go to the black rectangle. The black rectangle is the stuff between the else and the end of here. So that means in this case, we're going to line 4, okay? And the next line to trace is actually line 4 and not 3. Okay, in this class, we do not trace line 3, which only has a single word of else, because that line doesn't do anything. Okay, it doesn't do anything as far as the behavior of the program is concerned when you execute the algorithm. The line 3 serves one purpose, which is to separate the then portion from the else portion. That's its job, is as a separator. But as a separator, it doesn't do anything at runtime. It doesn't change a variable. It doesn't determine the true-false value of a condition. It doesn't do a single thing. So that's why we don't trace it. We just kind of say, okay, it's just a marker to tell us, okay, where does the else portion begin? Okay, line 4, and that's why we go to line 4 right away and execute the statement on line 4. Line 4 is an assignment statement, so we'll just do the usual thing that we normally do with an assignment statement. We evaluate the right-hand side, and then we use the value to update the left-hand side. Well, in this case, it's really trivial, right? X gets the value of x. Well, we still go through the same exercise. X has a value of 10, so the right-hand side specifies a value of 10. We copy that value to the left-hand side, which also specifies variable x. So variable x is now updated with a new value of 10. Now in this case, you cannot leave it blank, because every time you have an assignment statement, even if the update is using the same value, you still have to indicate it's an update operation. Okay, that's the convention that I'm going to use in this class. After line 4, where do we go? Well, line 4 is the only thing that is contained in the black rectangle here. So when we're done with that, we get out of the conditional statement, and there's nothing else to do. The conditional statement ends at line 5, and there's nothing after line 5. So we just say post here. We do not trace the line that says and if. Yep.
Do we leave any comment for?
No, you don't have to. If you want to write something about it in the comments column, you can feel free to do it. But this is what I'm going to expect. If this is if this was a homework assignment, that's that answer will get full credit. Any questions about what I just did? Yep.
Minor one, the parentheses.
Parentheses?
How important is that?
Not 100%. If you leave it out, it's going to be okay, as long as it is still clear. Which part is the expression and which part is the answer. All right. Any question?
I have a question.
Yep.
You left out line 2 and 3. So I guess what's really happening here? Because you didn't really use the if, then, else if.
Okay. Remember, it's a choice, right? A conditional statements represent a choice. So you can choose one or the other.
What are we choosing in here?
We are
Yeah.
choosing the side that is represented by false, the false branch, because the condition of the conditional statement, which is x is less than 0, is false. So that's why we choose to go in this path here, the path that is labeled false, and that's why the other path is completely ignored at this point.
So
Because
lines 2 and 3 just.
yeah, line 2 is not traced here because we are not going there. Because that's the whole point of a conditional statement is you have alternatives. But alternatives means you can only use one or the other. You cannot do both. And in this case, because of the condition, the result of the condition, we decide to choose the else branch, and that's why we choose to execute line 4. But as a result, the other branch is not going to be touched. We are not even going there into that path. Okay. Any other questions related to a conditional statement or how it is traced? No questions? This is all good? Okay. Let's move on to the next test case. Now with these, you can see that the precondition needs to specify a value for x, because otherwise I cannot compare an unknown value to a 0. Okay, so in this case, we do have to start with a particular value in x. So let's go ahead and take a look at this one. As usual, we have to repeat the condition itself, and then we have to indicate the result is what?
False.
The result is false. That is correct, because 0 is less than 0 is false. Okay? And as a result, it will follow the same path as the previous trace, where we will go to the else branch, starting on line 4. Line 4 is going to evaluate x, which has a value of 0 at this point, and then it will copy the value of 0 back to variable x. So x is going to get updated, quote unquote, with a value of 0. After that, we have nothing else to do in the else branch. It ends the else branch, but after the else branch, we get out of the conditional statement, and there's nothing after the conditional statement either, and that's why we are pretty much done, and we use post to indicate that we are done at this point. So basically the same path, as the previous test case, because 0 is less than 0 is false. Are there any questions about this particular trace? No? Okay. So now let's move on to the third one. The third one is starting with a different value in x. X starts with a value of -3. So once again, we start with line 1, and once again, we have to evaluate the condition so that we can choose one or the other branch. X is less than 0 is true. -3 is less than 0 is true. And as a result, if you look at the trail path, we have to take the branch that leads us to the blue rectangle, and the blue rectangle is the stuff between the if and the else. So what is the line number corresponding to that?
2.
Line 2, very good. So on line 2, we do have something that is non-trivial to do. We have to evaluate 0 minus -3 in this case. So what is the value of 0 minus -3? It's not -3. It's 3. Okay, so if I write it out, I think most of you will recognize this, because when I just talk about it, most people just go, oh, it's -3, but it's not. Because this is what we are evaluating, so you have negation of a negation, and it just flips the sign, and we have +3 in this case. And we're done, because after line 2, we are done with the then branch, get to the merge point, get to exit the conditional statement, nothing after the conditional statement, we're done. We use post to indicate this is the end of the trace, and that's it. Are there any questions about these 3 traces that we have done so far in today's class? Okay, any questions? Any questions I can answer?
I got it.
Okay. Well, if you have a question, you can just let me know, because probably some other people have the same question, and they're just too shy to ask. All right. So that's how we trace a conditional statement. And I'm going to also open up this document here, Conditional Statement Tracing Conventions. Okay, I mistyped the title, should be Conditional Statement Tracing Convention and not just Conditional Tracing Conventions, but it's saying the same thing. I'm hoping that as I read this part here, most people will feel, that's really boring. We know this stuff already. You kept talking about the same thing over and over and over again. That would be good. Let me know that you're bored, because that means we are getting this stuff. If people say, huh? We haven't seen anything like that. What are you talking about? Then I will start to worry, because okay, so let's see whether I have reasons to worry or not. The column labeled comments must be present and be the leftmost column immediately to the left of the line number column. Okay, so let's take a look at the trace here. We are talking about this column here, immediately to the left of the line number column. Okay. The line containing if or else if. Now in this case, we don't have any else if, so don't worry about else if, but we do have one line that contains if. It must be traced. So in this case, that would be, in the algorithm, our line 1, because line 1 starts with the word if. And the way you trace that particular line, you have to use the comments column to reflect the result of the condition. But you don't want to just tell me true, false. I want you to use a particular format, which is specified down here. Once again, this is a meta syntax, which means it is a syntax to specify the syntax of something else. So in this case, you want to repeat the condition from the conditional statement itself. And in our example, it was x is less than 0. So you have to copy that portion to the comments column. And because the word if is in boldface, so that means you just have to type it verbatim is. You don't have to make it boldface, just spell out is fine. And if you forget about that part, I'm not going to take any points off. But the most important part is you have to choose one or the other. Okay, if you see a bar between these options, okay, the curly braces are only for grouping purposes. It simply says, okay, this is a list of alternatives. Okay, and the bar, the vertical bar, is a separator of the alternatives, which means you have to choose one or the other. Okay, true or false. In other words, you have to tell me whether the condition evaluates to true or false. And that's basically what we have done so far, except I'm just trying to specify the syntax in a little bit more formal way. So that's basically what the rest of these points are saying. Okay. The lines containing else by itself or and if are not traced. So in our particular example, line 3 and line 5 are those lines, and we don't trace those lines because the purpose of those lines are only there to either separate one portion of a construct from the other portion of the construct, or to mark the end of a certain construct. And as a result, there's nothing to do, when we look at those lines, at runtime, and that's why they are not traced. All conventions already mentioned in tracing assignment statements are still effective, with the exception that there is now a new column, that is labeled comments. So everything that we have been doing before still applies. It's just that we have one extra column called comments at this point. So are there any questions about the convention of tracing conditional statements? No questions? Okay. If there are no questions about this, I'm kind of assuming that you guys know how to do your homework assignment, the conditional statement homework assignment. So we'll go ahead and go back to the notes and continue with our discussion of conditional statements. And I believe last time we kind of stopped only at this point, okay? Basically saying, instead of using yes, no, we're going to use true, false to represent the result of a condition. I believe we didn't quite get to this part here, okay? Comparison operators are basically the lowest level, the most basic operators that can give you true, false values, okay? X is greater than Y. Well, is it true or false? Okay, it will give you a particular answer, true or false. So I just want to make sure that we understand these operators and also understand how they are represented when you do not have easy access to the symbols greater than, less than, or greater than or equal to, less than or equal to, and so on. The first two items, I don't think we have to spend much time to explain that, greater than and less than. This one, I know it is a very simple operation. We're just comparing for greater than or equal to, but because we don't have a symbol on the keyboard for greater than or equal to as a single symbol, in most programming languages, they use the combination of the greater than symbol followed by an equal symbol to mean greater than or equal to in a comparison. So no big deal. The next one is about the same, less than or equal to. It is usually represented by a less than symbol followed by a equal symbol. Not equal to is, if you can type this, it's good, but if you cannot, then what are you going to do? In C and C++, it is an exclamation point followed by a equal symbol. And most languages derived from C and C++ would use this to mean not equal to, because the exclamation point by itself in C and C++ means negation, logical negation, not something. So exclamation point equal means not equal to. In most other languages, they use this really kind of weird operator to mean exactly the same thing, not equal to. Well, if you think about it, if I say x does not equal to y, doesn't that mean the same thing as x is less than y or x is greater than y? I mean, that's not equal to, right? So that's why it uses that particular symbol to represent not equal to. And that applies to Visual Basic, SQL, Pascal, and most of the non-C derived programming languages. And then we have the usual equal symbol. And the reason why it is the last one is because it is also a tricky one. Because equal to seems easy. I mean, surely we have a symbol on the keyboard for equal to. It is right there next to the backspace on below the plus sign, right? That's one key dedicated to equal to. So what is the big problem with equal to? Well, the big problem is in C and C++, if you want to express comparison, this equals that as a condition, you have to use double equal and not a single equal symbol. A single equal symbol represents assignment. You are evaluating the right-hand side and update the left-hand side. A double equal means comparison. You take the value from the left-hand side, you take the value of the right-hand side, you compare to see whether it is true or false that they are the same. So they're different. So now the big question is, what if you mistype in your program when you meant to compare, you type only one equal symbol? That's the question. Now, I wish the answer was as simple as the compiler would come back and say, this is the wrong place to have an assignment operation, and just come back with a line number and say, go fix it. I cannot do an assignment operation here. It is a part of a condition. Well, in C, unfortunately, you can have an assignment operation within a context that is expecting a true-false thing. Okay? In other words, a single equal symbol in many cases can syntactically take the place where a double equal symbol is expected or intended. And the compiler cannot come back to you and say, oops, you made a mistake here, please fix it. But what it will do is it will generate the code to update a variable instead of actually comparing the two sides of an equality check. You had a question earlier.
So the double equals is different from the arrow that we have.
Correct. A single equal in C is the left arrow symbol. A double equal is just comparison, which is a single equal symbol, in all other languages. So that's why C and C++ are not exactly programming languages well suited for beginning programmers. They're really not. And that's also why some of you saw a tab earlier to link to a book. This book is called C, and obviously I cannot remember the whole name, and that's why I'm searching for it. Rope, shoot, there we go. Now, I'm not sure about the quality of this book. If you look at the star rating, it's only 3.5 stars. And the paperback version is from 1 cent and up. So it doesn't look like it's a very sorted after book, But I do want to point out just the title of the book says something. Okay? The fact that somebody wrote a book with this title is telling you something about the C and C++ programming languages. What do you think? The title reads, "Enough rope to shoot yourself in the foot." And the reason is exactly that. The reason is C and C++ are programming languages invented by hackers for hackers. Now, when I use the word hacker, I'm not using it in the context of computer security, as in somebody's trying to hack into your computer. I'm using the word hacker to mean someone who's really proficient in the field and just want to get something quick and dirty and get things going again. Okay, so I'm using that word in that sense. In other words, it's not really intended for instructional purposes. It has so many things in C and C++ that can cause confusion, problems, and the compiler cannot check it because the syntax does not lend itself to checking for common mistakes. All right? So just watch out for these things when you guys move on to cisp300 because one half of this class, at least one half, is going to be bitten by things that I just talked about or throughout this semester. All right. So are there any questions so far about the comparison operators? No questions about the comparison operators? So let's go ahead and move on. Logical operators, and we'll talk about this later. Okay, so at this point we are done up to here, and this part, I think we have talked about this already. How to find the maximum of two variables. So this is the pseudocode representation, and down here we have the graphical representation as a trail map. So this is something that we just did earlier in this class using a different example. So are there any questions about this slide? How to read the pseudocode and map it to the logic that it is representing? No questions? Okay. If there are no questions, then we're going to move on to logical operators. Logical operator sounds like a complicated thing, but it really is not. Okay. Because we use it all day long. It's just that we don't use those words to describe the same thing. Okay, so we'll start with the first logical operator, which is also which is formally known as conjunction, informally known as the word "and" in English, A-N-D. Okay. So we'll skip all the way to the end of this slide here, and I'll go back and talk about the other stuff too. So the definition of "and" or the "and" operator is just this: true and true is true, false and true is false, true and false is false, false and false is false. That's it. Sorry? Say again? Oh, I didn't hear. I didn't hear what you said.
Nothing important.
Okay, nothing of importance. Okay. Is that consistent with your understanding of the word "and" in normal usage? And how often do we use that word "and" in English?
Rather often.
Rather often? And can someone give me an example of the application of this word?
I want an orange and a banana.
Okay. Well, in that case, it's not the same thing as a logical "and," but you do want both. Okay, that's very good. Yep.
That car commercial for the guys I think nuts and bolts or nuts or bolts, and who falls apart. You ever seen that one?
No, I haven't seen that one.
I know.
What if I have a little sign at the door right here before you come into the classroom, and I specify a condition and basically say only people who meet these requirements can get into this, can come into this classroom. Okay. So I will basically say the time has to be from 10:30 to noon, and you have to be enrolled in this class. Then you can come in during that time. So I'm placing a time restriction, 10:30 to noon, and also an enrollment restriction. You have to be enrolled in this particular class to get through that door. Any questions about that condition? So do you think you guys can come into this classroom according to that rule?
Yes.
Obviously,
Yeah.
right? This is the right time, and you are, enrolled in this class. Yep.
For those on the wait list, will we actually be enrolled soon?
Is that a question related to the explanation of the operator, or a question just for the enrollment purposes?
Yeah, just enrolled.
Yeah, you just
So
come
that's
up
a
to
good
me
idea.
and I'll give you a permission number. At this point, I'm not sure whether you can just do it with a permission number or you have to do a petition form. So you might need to get a petition form and fill it in, and combined with a permission number, you should be able to do it. But in terms of the logic, would I be able to get into this room if that's the rule specified?
No,
No, because, well, it is the right time,
but you're not enrolled.
but I'm not an enrolled student in the class. Okay, so that means with a conjunction, if at least one of the conditions specified is not true, the entire thing is not true. In order for a conjunction to be true, every specified conditions has to be true in order for the entire thing to be true. Is that making any sense? Now, when you think about normal usage in English, there's another word that spells out the same, that actually has the same meaning. Let me answer your question first.
I was going to ask, does this lead to exceptions?
Exceptions?
Like, since this, or I'm saying, like, in that scenario, you couldn't have it, but you can just write an exception on that. and
Or I
say-
can change the condition. I can change the condition to 10:30 to noon, and in parentheses, I can say enroll student or the assigned professor for that class. So I can change the condition to, right? But since I haven't talked about disjunction yet, because I don't want to introduce the fix to that problem yet. Okay? But there's another word in English that actually has the same meaning as and, but most people don't think about it as and. Which word
Also.
would that be?
Or?
No, or is different. Or is on the next
Also.
slide. Hmm?
Also.
Also is good. Okay, the word also, typically also means conjunction, because it means this and that. Both of those things have to be true.
Together?
Hmm?
Together?
Together. What about the word but? B-U-T. That actually has the same meaning. It's actually a conjunction. We choose to use the word but instead of and when the first thing and the second thing are somewhat contrasting. Then we use the word but they really mean the same thing. And but actually mean the same thing. Give you one example. Tak seems to know quite a bit about programming, but he's short. Okay? So if I use the word and, it would accomplish the same thing from the logical perspective. But the sentence would lose its,
Same.
yeah, exactly. Or we can say, Tak can definitely write programs in different programming languages, but he's not a good basketball player.
Nonsense.
Right? But in that case, I have to use a comma because the second sentence is a complete sentence.
Yeah.
But nonetheless, it is still meaning the same thing. So the word but is actually the same as an and from the logical perspective. So are there any questions about this slide about the meaning of conjunction, which is basically just and in English? If there are no questions about the meaning, I just want to point out the notation here. The mathematical notation looks like a little TP or inverted V. In a programming language, in C and C++, it is represented by double ampersand. This is not a typo, it is double ampersand. And this is also another case where if you mistype and use a single ampersand, it is okay from the syntax or grammar perspective, because there is an operator that looks like a single ampersand. So that's okay. But the meaning of a single ampersand is what we call a bitwise AND operator, which is related to a logical AND, but is not exactly the same thing. So the compiler would not complain. Anywhere you can specify double ampersand, a single ampersand can also be there in place of the double ampersand. But it means different things. Okay, a single ampersand means something that is slightly different from a double ampersand. The worst part about this is they look right. It looks right when you use a single ampersand. because that's how we would use it, right, with a single ampersand. So in C++ and C programming, you have to be careful about these operators because it's just confusing. Okay, so just watch out, but somebody is going to get bitten by this one eventually. In most other programming languages, like anything that is non-C derived, like Pascal, SQL, and so on, they just spell out the word and, which is a lot better. All right, the next slide talks about disjunction, which is a fancy word of or. This word, or this operator requires two sides, so we'll skip all the way to the bottom part here and just look at the definition of or. True or true is true. False or true is true. True or false is true. False and false, false or false is the only time when the disjunction is false. In other words, with a conjunction, you need both sides to be true for the entire thing to be true. For disjunction, you need both sides to be false for the entire thing to be false. So that's one way to look at it. Are there any questions about the definition of disjunction or? Is that consistent with your understanding of the word or in English when you use it in a logical way? Consistent, right? So in the example earlier, at the door, I have a post that says, you may enter between 10:30 and noon. You may enter if the time is between 10:30 and noon, and you are a student enrolled in this class. But I wouldn't be able to get into this class because I am the professor of this class. So I can change the condition to read as follows. I can change it to, you may enter if the time, if in parentheses the time is between 10:30 and noon on a Tuesday or Thursday. And, close parenthesis and open parenthesis again, but this time I have a disjunction on the other side. I can say then you are a enrolled student in the class or you are the professor teaching that class, close parenthesis. Now it's going to be okay because it's an or. I only have to meet at least one of the requirements in order to satisfy that portion of the requirement. What about either or? Would that be the same as an or? Nope. Either or is what we call exclusive or in logic. So it's not the same as a normal disjunction, which is just a regular or. All right, we have one more to go. One more, and it's negation, logical negation. Negation is basically just the word not, and for certain people, ain't. Same thing, okay? This logical operator is even easier to define than the other one because it only takes one value. Not true is false, not false is true. That's its definition. It's just you're flipping the polarity of the Boolean value. Okay? And negation has different types of representation. In mathematics, if you go take a logic class in a math class, as a math class, it is kind of like a cliff symbol, a bar, and then a drop. And in C and C++, it is an exclamation point. In other languages, it is simply spelled out as not, N-O-T. That's the negation operation. Do we have any questions at this point about comparison operators, greater than, less than, that sort of thing, or the logical operators, and or not? Any questions about those topics? No questions? Okay, so let's see how far we can push those particular things, and this is what we'll do. I'm going to give you guys a little in-class exercise. Nothing to turn in. I'm going to do it with you guys, but I do want you to kind of follow along and try to do it as I do it. That's a good font size. All right. So I'm going to give you a scenario, really kind of unreasonable scenario. And this is a programming language where the only less than comparison operator is given. You cannot have greater than, you cannot have less than or equal to, you cannot have equal to, you cannot have not equal to. You just have less than. Okay? So that's your restriction. So now the question is, can you translate all of the other comparison operators to just less than and a combination using disjunction, conjunction, and negation? That's the question. Can you live with just one comparison but use other things to help compensate for that? That's the question. Okay, so let's go ahead and take a look. Okay, so we'll say, okay, we want to express A is less than B. Well, since this fictional programming language has less than as an operator, so A is less than B is just simply represented as A is less than B. No problem, that's an easy one. What about B is A is greater than B? That's easy too, because since I only have less than and I want to express greater than, I just have to flip the two sides, right? That's an easy one, because A is greater than B means B is less than A. Fine, not a problem. What about I want to express A is less than or equal to B? Remember, you can use logical operators. How do you use logical operators to help, in this case? What about something like this? A is less than or equal to B is really saying it is not the case that A is greater than B. Would that be the same thing? A is not greater than B. Is that really saying that A is less than or equal to B?
Yeah.
Yep. Yep, that works. Cool.
So B is not less than A. So B is not less than A, since we're only supposed to use less than sign.
Oh, right. Okay. You're right. Good catch. All right, so there we go. And then the other one is just flipping this. A is greater than or equal to B, and with this one, it is just it is not the case that A is less than B. Okay. All right, because that's just symmetric. We just flip the sides. Okay. Those are the easy ones. What about A does not equal to B? And you are allowed to use any number of logical operators.
You use an and. Say both of them.
What about the or?
That's the,
Yeah, the-
A
You can say A is less than B or B is less than A. So I'm reducing everything to use only less than. Okay, great.
Not.
Hmm?
Can we put not A equals B?
Not A equals B.
Well, then we're not using the less than sign.
But you cannot use equal. You can only use less than.
Oh.
Yeah, these are brain teasers, right? What about A equals B? Well, there's an easy way to do this one, because you can just say, oh, we know what is not, we know what is different from, right? Just put a negation in front of the whole thing, and now we have equal to.
That was easy.
All right, so we can. So in other words, if I want to give people a really minimal brain-teasing type of programming language, I only have to supply less than. And then all of the other comparison operators can be implemented just using less than. Are there any questions about this? No questions about why would an insane computer scientist be doing something like this, trying to use the least amount of something to recreate everything else?
Sounds like efficiency.
Efficiency, very good. Well, this has something to do with RISC versus CISC. RISC stands for RIS, RISC spells RISC, which stands for Reduced Instruction Set Computers. Okay, as opposed to CISC, which stands for Complex Instruction Set Computers. Okay, the difference is how much silicon do you want to use for your processor? That really is the question. Okay. The Intel processors that you have in your typical PC, Mac, and most of the other computers, the non-mobile computers, they all use a CISC architecture, which means the computer chip is relatively big, it's powerful, but it's bigger. The cell phones typically use a RISC processor, which means if you look at the physical size of the die inside the processor chip, it's pretty small, Okay, so the question now is, should I use a bigger processor die that is more powerful, or should I use a smaller processor die that is smaller? Well, the question is, what are you going after? Okay, that really is the question. Well, with cell phones, we want a smaller die because the smaller die means less power consumption, so you don't have to recharge your phones 5 times a day. And I know some people do that because some people watch TV and everything else on the cell phone, so every 4 hours they have to recharge. And because the people want their cell phones to be really thin, so they don't, so there's not much space to put the battery. I can charge my phone once every 2 days under normal use. And it's a smartphone. I'm not using a flip phone, okay? I know some of you are thinking, oh, you have one of those ancient flip phones. And those things can last a week, right, easily. And I miss that. You can look at the thickness of my phone. It's not the phone itself, it's an extended battery. And I find it to be useful. It's heavier, it's thicker, but at the same time, I don't have to worry about running out of battery for 1 day. Okay, this is good for 2 days at least, for me. And then the other thing about CISC versus RISC is when you're dealing with a data processing center. Okay, I'm pretty sure most of you know what is a. Do you know what is a data processing center? That's where they put a lot of computers into a small space. They use it for heavy-duty computations, like for physics, particle simulation, animation. Like Pixar, would run their animation film in one of these data processing center to render the graphics, right? So the question is, what is the limiting factor that constrains how much processing power can they pack within a data processing center? What do you think?
Limited to how much space or how big the things are that.
What are they running out first? Okay, that really is the question. What is it that they're running out of that limits how much processing power they can pack?
Space.
Not it's not space.
Energy.
Not energy. They can. Well, energy is a big thing, but that's not a limitation. That's actually partially why Google is now a certified power supplier. They can actually sell power and own power plants. But that's not the reason. Anything else?
Time.
Going everywhere.
Is it time?
Time? No. Heat. Okay. Heat extraction, to be exact. Okay. Heat extraction is the limiting factor. In other words, if you pack a lot of heavy-duty, powerful computers into a small space, how do you get rid of all that heat that is generated? As it turns out, that really is the limiting factor. Okay, how much heat can you extract out of a space is the limiting factor of how much processing power they can pack in the building. And why would that be brought up when we're talking about CISC versus RISC?
Because the heavier duty chips will create more heat.
It will create more heat, but it is also more powerful. It can get more things done.
It can also melt it faster if it actually works that hard.
Well, you have to look at what we call MIPS per watt rating. In other words, how much processing can be done not per time unit per second, because that used to be the holy grail, right? The more processing or the more processing per second, the better. But now people found out that that's not really necessarily the most useful thing, because we cannot extract the heat fast enough when you have CISC processors. So now they're going after MIPS per watt, or how much processing can you do per, well, actually this is the wrong, but this is the right unit, never mind. It's the right unit, because they are both per unit of time, so it is the right unit. So that really is the benchmark they're using now to select processors for processing centers. And as a result, RISC architectures turn out to have a better MIPS per watt rating than CISC processors. So even though each one is smaller and less powerful, but if you pack a whole lot of those things, they can give you more processing power per watt of heat dissipation than CISC processors. And so data centers, IBM has switched to RISC processors for years in their mainframe computers. So they're not using Intel, i7 or Xeon, processors. They are using PowerPC type, of processors in their, data centers. And that's partially, I mentioned this because, the question is, why do we want to reduce everything to really, really simple operations? And that partially is one of the reasons. Because you can save silicon not implementing the logic of all of those operators. You just spend silicon to implement one single comparison and do everything else, using that one single operation. All right.
Roll.
Thank you. And I keep forgetting that too. This is the first class. Today is the 6th. Yep.
First class. Oh, wait, the second class of the day?
This is the second class. Yep.
I thought you said first.
Yep.
This MIPS measurement of repeat or something.
No, MIP stands for million instructions per second.
Okay.
So if you want to change the unit, you can actually change it to million instructions, but then the other one also cannot use a per time unit basis, so that would turn it into joules, which is the measurement of energy. So million of instructions per joules is also a equivalent measuring unit. Okay. So are there any questions about the discussion a little bit earlier? Nope, no questions. All right. So with logical operators, now we can tackle a new problem. Okay, so I'm going to give you guys and myself a new problem to solve. We were able to find the maximum of 2 variables and store the maximum into a third variable. Okay, that's done already. What about if I give you 3 variables to start with? I want to find the maximum of those 3 and then store the maximum in a 4th variable in this case. So I give you the variables w, x, and y, and I want to store the maximum into z. That's what I want you to do. So how would you write an algorithm to do it? Well, there are several ways to do it. Yep.
I was going to say, it's kind of similar to this, but if saying like x is bigger than y and z, I mean, if w is bigger than x and y, then do this. If not, do that. In the else being if y is greater than x and w,
Okay.
this otherwise, and then you get all 3.
There are at least 2 common solutions to that problem. Okay, and you're describing one of them, which requires the way you describe it seems like you're nesting conditional statements. So we'll defer that discussion when we talk about nesting statements. But right now, since we are not nesting statements or having conditional statements inside conditional statements, let's think about it. Okay, you have 3 variables. I give you 3 variables, w, x, and y, and I want to find the maximum. Well, just because of the definition of maximum, I know one of them has to be the maximum. Does that make any sense?
Yeah.
Regardless of the values of the 3, one of them has to be the maximum. So that means if I look at the overall scheme of things, I can say sometimes I want this because w turns out to be the maximum of the 3. Sometimes I want this because x turns out to be the maximum of the 3. And sometimes I want this because y turns out to be the maximum of the 3. Is that making any sense?
Yeah.
So I need branching again, but conditional statements up to this point only can choose one of 2 ways to proceed. Now we have 3. So it doesn't seem to jive with what we can do with conditional statements. But you know what? Let's not worry about all of the options. Let's just think about one option for now. In other words, how do I confirm that w is in fact the maximum of the 3? Let's just focus on one thing. In other words, I am here, I know there's a branch, and I know there's an alternative somewhere, But if I really just want to focus on this side and say, when can I use w as the maximum, how would I express this condition that w is in fact the largest of the 3? Or one of the largest of the 3? Well, think about it. In other words, if I put a sign here as an expression to evaluate, as a condition to evaluate, how should I formulate the condition to confirm that W is the maximum of the three. I'm opening this up because it's going to be a little longer. Yep.
W is greater than X and Y.
Okay, W is greater than X, and W is greater than Y.
A little bit bigger than the sign. Not structurally intact.
And I'm using the wedge symbol to mean conjunction too. Okay. Well, that's almost right, but we'll just say that it's kind of right. Okay. This is good because it will lead us to the next topic, which is how do we know the algorithm is correct? Okay, because this is correct most of the time. This approach is it will work most of the time.
Until one of them equals it.
Yep. Okay, so for the time being, we'll just say that W is greater than X and W is greater than Y confirms that W is the maximum of the three, and as a result, it's perfectly fine to use W to update Z. After this, we just get out of the conditional statement. We are done. Our mission accomplished. Okay, yeah. Okay, what if this condition is not true? What if this is false? Well, if that condition is false, we have just confirmed one thing, that W is not the maximum, right? So if W is not the maximum, then the maximum is between X and Y, right? So in this case, I could, use a simplified condition here and just say, well, the result is just, between X and Y. So if X is greater than Y, then we'll use X as the maximum. And if it is false, so this is true, this is false, Z will get the value of Y. And every single one will merge at the very end here, and then we get out. Is this picture making any sense?
Yeah.
To solve the problem that we want to solve? Okay. All right, so if we do it this way, it's actually correct. But then someone is going to say, well, it shouldn't hurt if I change this condition so that we double confirm that X is greater than W. Okay, well, the fact that we are here, it kind of confirms that. Or does it? It's not. Okay, but we'll just kind of use this formulation here and say, well, we'll double confirm that X is greater than W also in order to confirm that X is the maximum. Okay, it doesn't seem to hurt anything, right? It seems to follow along. The logic seems okay, maybe a little bit redundant, but doesn't seem to hurt. Okay. So let's say we write a program like this, and how do you test this program? How do you know the program or this pseudocode is correct? That's a big question, right? Because before you publish any software, you really should have quality assurance to make sure that your program does work the way it's supposed to. Yep.
Basically just try to put something in that will screw it up, or
Okay, we try to put in some values and see whether it works correctly for those values, right? Okay, that's a good plan. Okay, but before we go even that way, let's take a look at how we express this kind of logic, and it's already in the notes, so that's why it's easy. I don't have to actually write it on the whiteboard. The construct is called a multi-branch conditional statement. So it looks kind of like this. We have C1 here being that big mess. W is greater than X and W is greater than Y. C2 is the other condition, which is X is greater than W and X is greater than Y, and then the rest are basically the same. Are there any questions about this? Okay, this is the pseudocode representation of this logic here, and there's a picture of this too later on. And I will show you that example. Okay, so that's basically the else if condition, and here we have the same picture as what we have here. Okay, except it's annotated a little bit differently. Okay. And the pseudocode representation of this is that. I can't find the text representation. Right, there you go. Okay. So this is the representation of the pseudocode, except instead of greater than or equal to, we have greater than in the picture. So the big question is, is that really that important, greater than or equal to versus just greater than? How much difference is it going to make? That's the question. We have 4 minutes left. Let me just kind of do this part first, and then we'll finish this next time. And the usual thing I would do is I would give you guys a brain teaser for those of you who want to take on the challenge. So the challenge is, if I write this program like this, okay, the way I'm specifying here on the whiteboard, if w is greater than x and w is greater than y, then z gets w. Else if x is greater than w and x is greater than y, then z gets y. Else z gets, oops, this one is wrong. Z gets x here, z gets y here, and if. So the question I have for you as a brain teaser is, if this is my pseudocode, how would you construct a test case to prove that this does not work all the time? So I'm already giving you a partial answer, which is it's not working, it's not going to work all the time. The question is, what is the test case that you will need to prove that it does not work all the time? Yep.
The same number for all three.
Well, if they're all the same, then it's going to work just fine, because any one would be the maximum. If you have 1, 1, and 1, then 1 is the maximum. That would not matter at all. So the question is, how do you...
W would have to be equal to either x or y.
W has to be equal to x or y, and both are larger than the other one, the third one. Yep. That would be the test case that will break this code, because it would not do what it's supposed to anymore. But when you just look at the code, it's not obvious. In other words, if you are not looking in the right way, and you're just throwing random numbers at it, you can be throwing random numbers at it all day long and not catch the case when it does not work. Okay? So the way the analogy that I use in my classes is like this. I need a different color here. Okay. If you look at all the possible cases that you can throw at an algorithm, okay, let me erase this one here. If you look at all the test cases you can throw, it's a really huge area. So I'm just going to use this blue circle as the entire space of possible test cases you can throw at an algorithm, which usually is really big or even infinite. Okay, so this is a huge space. I will use the black pen to mark the ones that will, that the algorithm will fail on. Okay, so the black dots means, this is a case where the algorithm does not work, or it would be incorrect here, 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 and here. Okay, so now the question is, you don't know where the black dots are to begin with, and you're trying to find them, right? You're trying to confirm the existence of the black dots and say the algorithm is incorrect. And you are now I'm gonna face this way, and I'm gonna throw dots backwards. Okay, so the question is, what are the chances that a dart will hit a black dot, and I turn around and go, oh, that dot is black, this algorithm does not work?
Very slow.
It depends, right? It depends. Okay, sometimes maybe it's not that difficult, but other times, maybe it's really hard to do it. So if I throw backwards, 20 million dots, and they, for whatever reason, none of them landed on a black dot, can I then conclude the algorithm is correct because it works on all cases?
No.
No, I cannot. Okay, so there is the big problem of software verification. Okay, how do you know an algorithm, a program, is going to do what it is supposed to in all possible cases?
You don't.
Well, this is going to lead to a discussion that most students in the past at least, do not like. It is called pre and post conditions. It is basically the math part of computer science, because we are going to use techniques to prove it once and for all, whether the algorithm is doing what it's supposed to or not. Okay, and that's going to be a few weeks down the line, so we don't have to worry about it just yet. But it will be here soon.
But it's coming.
I'll see you guys next week. Have a nice weekend.
So
You need a permission number?
I think that if I just don't get a petition,
Okay,
that
so-
would, I'll know